So without further ado, would I ask Professor Vdovina to talk about higher structures in algebra, geometry, and C3 algebras.
Yeah, thank you very much, Mark, for that introduction, and many thanks for the rest of the organizers who allowed me to speak. Right, it's usually organizers shouldn't speak at their workshop, but this is kind of more wrapping up and just showing some ideas. So it's there are plenty open-ended projects, and so you see that even on my title page there is a picture of a 4 cube, and this is kind of indication that indeed we can explicitly construct higher rank graphs for every k. So like the probably first official series is in our paper, Nadia, which is already for a couple of years in archive, already accepted in geometry dynamics. But also, like I was following many talks at this workshop, and I realized that there are even many more complexes, like which appear in various papers of myself with various collaborators. And then actually they all give higher rank graphs for every case. So my task now is somehow explain the constructions. And somehow what I also realized that it's not that just we work in different fields, we also all think in different terms. So that's why it's really important to find all those connections. And this is the plan, and to talk about buildings, of course, without the formal definition, because the formal definition, it's like half of a year course, and probably still the life doesn't become easy after this either. So I'm going to give like very explicit construction of arithmetic lattices and product of trees, because they are very relevant. They give explicit examples of higher ranks of every k. And of course, I couldn't resist to put Jan Baxter equations after Fabian's talk yesterday. And yeah, then we will see how it goes. So buildings were introduced by Jacques Titz in the 50s, but if you look at the initial papers, they are very abstract algebra, Lie groups, and one cannot recognize K graphs there at all. But what is good about buildings that they have algebraic, analytic, number theoretical aspects. There are many aspects, and if you jump from one aspect to another, you can get new results. Actually, I didn't put geometric because it's like obvious. And what do you need to know about buildings? That they consist of chambers and apartments satisfying certain axioms, and each apartment is a set of chambers. But what is good straight away, we have an elementary example of a building, of one-dimensional Euclidean building, which already appeared in many talks. It's a Kelly graph of a free group on 2 generators. It's kind of four-valent graph. You can think about it as like chambers are edges and apartments are infinite paths in this infinite graph. So like that's why we go to the dimension 2 straight away. And when I say polyhedron, I mean that we have a set of polygons with some letters on the boundary, and then we identify the letters, the edges with the same letters respecting orientation. So these squares are not kind of commuting squares from the K graph. They are geometric squares. And probably I should remind an example from algebraic topology. When you have a square with the word A, B inverse on the boundary, then when you identify the sides with the same labels respecting orientation, you get a torus. And then you can think about one label as A and another label as B. And of course, it's kind of nice standard construction. And then you also have that your fundamental group of the torus, which is just kind of abelian of rank 2, acts so compactly on the plane tessellated by equilateral squares, right? So I will keep this picture in mind because we are going to use a very similar idea to have a like complex and its universal cover and the group, fundamental group of this complex acting on the universal cover, but just our polyhedra are not going to be embeddable in a three-dimensional space. So you cannot draw them so nicely as you draw a torus glued from a square. So that's why we have to kind of analyze these words which are written on the boundary of the squares. And you see that here I deliberately chosen an example such that the words don't look like commuting squares at all, right? But nevertheless, there is a two graph associated to this geometric construction. Just every square, every geometric square has to be replaced by 4 kind of oriented squares. Then you get a K graph. But actually, the K graph here, you need like, it will be like 16 commuting squares. Okay. So are there any questions so far? Because of course, like the goal of my talk is like to bring more people to geometry, right? And so that's why I would like as many people to, yeah.
So I'm just, what are these squares representing? You don't actually patch them together.
I
Like
patch them. I said that we identification, I patch them together indeed.
you can't tile the plane with these.
Very good question, Jack. We can, and it's not just one plane, but it's uncountably many planes.
I just can't seem to make it go horizontally more than 2.
No, you can, because you see, respecting orientation, those squares, that's why I kind of, you can flip, you can do whatever with them. You flip, you can flip them, you can rotate them. That's why I said that, like, deliberately they are not commuting squares to exactly to have this type of questions. You can do whatever. It's also when you talk about like tessellation of a plane by a commutator, you can also start from here or from here or from here, doesn't matter. So it's in geometry, when we talk about fundamental groups of complexes glued from polygons, we think about when we talk about geometric square, we talk about all its cyclic permutations and actually flips as well. So that's why it's, and indeed, how I think about those polyhedra, that we identify them, like the sides with the same labels are identified. And also respecting orientation, right? You have to get them, you need orientations to match. And like you see here, you have like four occurrences of each letter. So of course, this complex will not, you cannot draw it, right? The complex, actually this particular complex will consist just of one vertex and 4 faces, and they will all be kind of glued. And that's why we need those. So first of all, this way to think about polyhedra by a collection of words is very useful, because you don't need to draw it, right? Because like saying this word, okay, fine, you can draw a torus anyway, but to keep track what is glued with what in higher dimensions, like it's in a dimension 2, still you can probably guess, but if you go to dimension 3 and higher, no way, you have to keep track what is glued to what. Yeah, and that's why we need those additional definition. So it's a like a link. Link is also, the word link is overused in mathematics, similar like to lattice. But here the link is kind of your local structure at the vertex. But so what you do, like take a sphere of a small radius at a point over the polyhedron, and then the intersection of the sphere with the polyhedron is a graph, which is called the link at this point. Because we stay in dimension 2, in dimension 3, but in dimension 3 and higher, the link is also the intersection of a n-dimensional sphere with your complex. But here, just let's at least about dimension 2. So imagine that in this vertex, you take a black sphere, and the intersection of this sphere, it's just one vertex and 4 edges. So the link, like if you say there is a link at the vertex, it doesn't mean that you look at the edges coming from the vertex. It means that you consider a sphere centered at this vertex, and then the intersection of your polyhedron and the sphere is a link. So the link here is just one vertex and 4 edges. And now an exercise, if you consider this torus glued from a square as a polyhedron, and we look at the sphere of a small radius centered at this point. So what is the link? What is the link? Like imagine like here, you get a, let's take another color, like green sphere, and it will intersect the torus and this graph, which is just 4 vertices and 4 edges. It's kind of cyclic graph. It's not a very complicated link, but each edge which is incident to the vertex will become a vertex in your link, and each face will be an edge. Okay, so you keep track of the local structure of your complex by looking at the links. Okay. Any questions?
This link is not sort of unique, right? If
So the link, if you have a polyhedron, right, then the link is unique. It's intersection of the it's like it's a graph, right? It's of course up to graph isomorphism. Of course, you cannot say about the lengths and so on, but like here, the link is always this graph, right? So it's, yeah, let's have another elementary example saying a tetrahedron. So another exercise, right? It's what you do with students. The first problem was not solved, so you given a slightly easier problem. So imagine a tetrahedron, and what is the link at this vertex?
Yes, 3.
Yeah, very good. Yeah, so like Adrian had an independent study course with me this year, so it's like you see that. So the link here, right? It's just a cyclic graph with 3 vertices. And actually, there is even a deeper meaning of the fact that here we get, for the torus, we get a cyclic graph, and for the tetrahedron, we get a cyclic graph, because what is topologically a cycle is a S1. It's a sphere like S1, and it tells you that the torus is a manifold, right? That like tetrahedron and torus, they are manifolds, and it's the links of manifolds are spheres. But actually, we need highly singular spaces as links to construct buildings. So, and this is somehow explains my title of the talk when I say like higher structures. What does it mean that the higher structure, it's not it's not just a dimension of your complex or like variety or whatever, but it's also this kind of the branching, the branching like in a tree, right? We're all happy with trees, right? That there is a lot of branching. But when you think about like higher dimensional branching, you get into such trouble straight away in the already in dimension 2. And even if you look at manifolds, right? Of course, there is a lot of mathematics about like manifolds of higher dimensions, but they are kind of nicely behaved, like even manifolds of higher dimension, they are nicely behaved because their links are spheres. Okay, I hope that yeah, I will not put it an exercise, right? I could say that, okay, let's take the example on my first slide and what is the link? So actually, if you glue those 4 squares together, then you get a complex with 1 vertex. And the link at this vertex is this complete bipartite graph. So what does it mean, complete bipartite? It means that there are vertices of 2 colors and there is no edges between the vertices of the same color, but everybody else is connected to everybody. And it's kind of small reminder of a terminology from graph theory. A diameter of a graph, it's the maximal distance between 2 vertices. So here it's 2. If you pick any 2 vertices, then the maximal distance is 2. And the girth is the length of the shortest cycle, which is 4. So, right, it's like, so those things like diameter, girth, we would need. And actually, why we need this kind of diameter and girth, just kind of intuition, I can tell you what happens with this link in this picture. The link, you can kind of keep track of it. And that here it's just a coincidence that the girth is 4. And this girth 4 tells you that you will have 4 squares which meet at each point. And in a way, the sum of the angles is 2 pi if you talk about equilateral squares. So those links are kind of important when you have like highly singular branching spaces, like high dimensional analogs of trees. Then your link tells you how to keep together your squares in the apartments. Okay. Yeah, any questions? And now let me tell you like a theorem of Ballman and Breen in mid-90s that let's have a compact 2-dimensional polyhedron. And if all links are graphs of diameter m and girth m, then the universal cover of the polyhedron is a 2-dimensional building. So it's in a way similar to this picture here, that the universal cover of the torus is a Euclidean plane isolated by equilateral squares. And in a way, here you can think about this plane as elementary building, because what is important for buildings, like what I said, that we have chambers and apartments, but then what is the very important property that when you have any 2 chambers, there is always apartment containing both of them. And here it's nice that you have only 1 apartment. So of course here so squares are chambers, and every 2 squares are contained in 1 apartment because there is only 1 apartment. But if we look at the universal cover of the polyhedron glued from 4 squares I showed before, then the universal cover is already like non-trivial. It's like for experts, it's like A1 tilde plus A1 cross A1 tilde building. And there are uncountably many apartments contained in this building. And actually, this is a reformulation of what in Balmans and Prince paper. They have completely different terminology, but it's totally abstract. And then how I came to this area, I started like to construct such kind of polyhedra in like very explicit way that by defining certain families of words with some properties which ensure you that you will get the links which you want. And actually, if you have like even number of sides, like I had like very nice, there are very, very nice, easy series of examples which you get quite fast. But then it turns out that still, if you need some extra properties, then you have to work harder. But even those, like I have a paper in Mathematische Zeitschrift and in 2002, and even using this kind of the most elementary construction, one can still get interesting two graphs. So my student, former student Sam Matter published a paper, I think it's Bulletin Australian Math Society, how to get like K graphs, and then they also like the structure of the buildings also helps to compute the K theory of the higher rank graphs which come from this building. Yeah, so it's another, probably like another motivation to probably understand what we are doing, because if you have this explicit construction of a like complex, then you can get a K graph from it, and then you can compute the K theory. Of course, you have to work a little bit in each step, but nevertheless, this kind of explicit words give you a way to arrange your elements of the system algebra. Okay, any example, any questions about the two-dimensional case? Because I think we're already ready to go to the K3 and higher, because yeah, like there were a couple of brave people who were drawing cubes, right? But it's it takes some time to talk about to explain this kind of cube condition and so on. So that's why I like already want to start with this. So just please now ask questions about two-dimensional case, right? Okay, great. Everything is clear. So now our buildings will be like, will consist of 3D chambers. And yeah, so the apartments are tessellations of, think Rn by ND cubes. Okay. So, of course, I don't want you to understand every line on this slide. It's just to say, to show that it's like so what I'm going to do now, I'm going to construct like for dimensions like 3 and higher cube complexes such that they are universal covers are buildings, or in this particular case, it's a Cartesian products of trees. And so what do we do, right? Then even in 2 dimensions, we have to take care how our squares are glued and so on, but it's still like sometimes it's computer search, you can get some examples. But for like dimensions 3 and higher, it's really hard to get something irreducible. Later on, probably I will tell you about this kind of notion of reducibility. But then, so here what we are interested in, some kind of numbers. We have to have some kind of set of indices which we will put on our alphabet. So in a way, in my first example, even with those 4 squares, those 1s and 2s, there is a reason. Actually, this is like the smallest case of the computation here when you put q equal to 3. So it's those like 1s and 2s, they were not kind of just out of the blue. No, they had a very precise meaning. If you put like q equal to 3, then you will get the coefficients in my first example. And here, just to show that we have some computations in finite fields, right? So you have like saying two i's, I and j in the finite field, and then you do certain computations, and then we have also like an extra parameter delta. So it's in a way to say that there are many possibilities, even if you take like a pair of elements in your field, then following this procedure, you will get two other numbers, this L of ij and K of ij. So far, we're just kind of saying that we have this kind of very explicit algorithm. This even takes no time to program it. I think that, yeah, my former student Sam Matter has even a program how to get those groups, because it's really just very easy computation. And the proof that it works, it's like involves quaternion algebras and so on, higher kind of hardcore number theory. But here it's just kind of you take two numbers, I and j, and then there is a formula like of this Lij and Kij, which are defined just using I and j and computation in a finite field. Okay. So now why I needed it, because now straight away we have groups, and those groups already can be used to get three-dimensional and higher complexes and subsequently higher rank graphs. So let's see how they look. So there are like a couple of parameters, and there is this number m, which is also kind of easily computable, and any number of trees can be encoded in this way of this kind of m. And then what we do, right? That's why I was talking about like K and L, that we have the relations. We say like AI AJ equals to this A Kij Lij. But again, of course they look very much like commuting squares for the higher rank graphs, right? And it's like almost kind of tempting to say, okay, probably this is already the higher rank graph. But it's not. Again, like to get the higher rank graph, you have to replace each of them by 4 directed squares. So each geometric square has to be replaced by 4 oriented squares. But those relations here just kind of to have it means that A with this index is inverse of AI with this index. It's just for the for the notation, right? Of course, we could write inverses, and here we would have much kind of more complicated presentations, but actually it's just, yeah. So actually those groups, it's all very often in number theory, you have like odd primes and 2. So like this construction here, it's for odd primes, it's really nice. They are all torsion free straight away, but with even, you get a bit of torsion. You can get rid of it. You can go to a subgroup of index like 4, which will not have torsion anymore. But nevertheless, like the groups which we start with have torsion. But then the structure is very similar and so on. But the difference, it's like this even case. My collaborator here it's like Raguna Perom Stix and myself, and Niti was a student of Jakob Stix, and his whole thesis was just to get this even characteristic, because like from number theoretical point of view, your life becomes much more difficult. So you see that it's kind of, there is a ingredient coming from completely different field, which tells you how to glue your squares. And okay, now this is the easiest example of p equal 5, because like p equals 3, we don't have a 3-dimensional example. It just for whatever it's to get this kind of interesting cube complexes which lead like to k graphs from 3 and higher. You need a bit of room. So probably this is like one of the reasons why in the theory of k graph algebras, it's not that many examples, because you cannot get them just accidentally, because of course a lot of small examples you just get accidentally. No, here, like between also in this field of high rank lattices, and actually lattices, it's in a different sense. Lattices here, it's discrete subgroups of Lie groups. And so between like about 2000 and our paper, there was a gap between big dimensions 2 and 3, right? Because you have to do something, but now we already have something very, very constructive, right? We have a set of squares, and according like to our paper with Nadia, how we get a k-rank graph from it, each square is replaced by all its cyclic permutations, and this is how you get your commuting squares, and then you put them together, and by magic they indeed fit to a three graph. Okay, any questions? Okay, and this is like, I also want to define something, okay, I cannot say completely new, but I didn't see it in the community of the higher rank graphs yet, but I think it has, I already have some motivation, which I will explain a little bit later. It's to look at the spectra of the graphs, because of course, like if you have a higher rank graph, you can think about its like one-dimensional skeleton, which has several colors, and actually you can define like its spectrum, like in spectral graph theory. So a bit of motivation that there is this kind of bound, and I think Alon mainly working in like theoretical computer science, and the motivation was coming from theoretical computer science, that if you look at graphs and with a like large diameter, so we already defined the diameter is the length of the shortest cycle, and then asymptotically the lower limit is 2 square root of q. So it tells you that when you work with concrete graphs, you shouldn't try to get something more than 2 square root of q. And this is the definition of a Ramanujan graph, that the adjacency operator, actually this is the second eigenvalue, because it's again an exercise. If you have a regular graph such that every degree, the degree of every vertex is q plus 1, then the highest eigenvalue is going to be q plus 1, but the second eigenvalue is the one which people are usually interested in. And Ramanujan graphs are those which the second eigenvalue is bounded by 2 square root of q. Okay, and the first non-trivial examples were due to Margulis and Lubotsky-Philipp-Sarnak, and Lubotsky-Philipp-Sarnak probably is like more known construction, because the paper of Margulis was published really in some kind of proceedings of some institute in Moscow in Russian, which like probably people in the West like didn't know too well, but yeah, I remember that people were like talking about it a lot. It's really kind of ingenious construction, and yeah, but then it's really great that what is good in the audience of operator algebras, that for people like don't mind when you talk about like operators on graphs, right? That like in group theory audience, you have to always like explain what is this and so on. But here it's like somehow what is the idea, how we talk about this kind of high dimensional Ramanujan cube complexes, that in each direction, so I was already telling that we have those cube complexes with edges of several colors. So in each direction, we define an adjacency operator. And what is nice that they commute, and there is a simultaneous spectrum. So of course, like in some work of like Aidan and with Nadia and with other many collaborators, you have this, you were already looking at the spectrum of the higher rank graph, right? But just I think that one can look at it a little bit even further to look at the second eigenvalues, because like you mainly looked at the first eigenvalue, but actually I think the second eigenvalue is also interesting. Okay, but then we just say that it's a Ramanujan complex if in every direction we have this bound like 2 square root of the adjacency minus 1. And what is good that those quaternionic groups which we constructed with Roman sticks give us, actually not all of them, you have to work a little bit, also you have to keep track what's happening, but many quotients of like products of trees by our groups give those like higher dimensional expanders, and also like it's a good good source of the higher rank graphs. Okay, any questions? Okay, then no, I think I'm doing okay with time, so let's connect it to the Yang-Baxter equations. And yeah, so those solutions, I call them like Drinfeld-Manin solutions of Yang-Baxter equations, because I was going like to basics of the history of this Yang-Baxter equation, because I kind of got an idea that they must be related to those like cube complexes, because they were like this kind of behavior. It's really like your compatibility conditions like on the cubes. And then, yeah, it was during lockdown when we all had time to think about topics which we usually don't think, right? And yeah, but then it was strange that this condition which yesterday Fabian defined as like non-degenerate. Most of my solutions don't fit to it, but some of them fit, but some don't, right? And then I was lucky that I was able to talk to Yuri Manin 4 years ago. Unfortunately, he passed this year. And then I asked him like how it even appeared, because of course, like most of the work is kind of attributed to Drinfeld, but in the basics they were discussing it. There are a lot of papers like in Russian in some obscure places. Then I was really going to this basics because I wanted to know how this appeared, why suddenly people are like, if you Google Yang-Baxter, probably like you have this experience, Fabian, as well, that if you put Yang-Baxter, you have like zillions of papers. So you just, yeah, and actually it's, yeah, it must be something into it. And then I asked Manin if I can, so he was happy that he was okay that I called it Drinfeld-Manin solution, because you don't have this extra condition of being not degenerate, because then I checked that, because he, like Manin told me that it's not a condition which comes from physics or whatever. It was just, it looks like almost like people who were working on it, they were just interested in this class of solutions, right? There is no kind of a special reason after it. So, okay, so this is the Yang-Baxter equation. And so what is new somehow, if you look at if you get those solutions from complexes, we get some new kind of invariants that we can really show that the solutions are really new, because as I mentioned, there is a lot of literature on this subject. So how you show that solutions are new. And yesterday, like Fabian defined the so-called like structure group. but the group which you will get the fundamental group of the complex behind it, it's even like a better invariant because you can distinguish them better in a way. So now let's say how we get the solutions. Yeah, because this is what Fabian already told us yesterday, how you pass from this like more either set theoretical or Drinfeld-Manning, how you go to the actual ones, to the linear operators, right? That you just with your set, right? Because if you have like set theoretic, you have the indices for your sets, like for your set X, but then you just index the basis elements of the vector spaces by those set theoretic solutions, right? You just span it. Yeah, and now straight away I will tell you how you read the solutions of the Young-Baxter from the cubes. So of course, like yesterday, Fabian mentioned the paper of Dilian Young when she has like this interplay with higher rank graphs and set theoretical solutions, but it's not necessarily you get new solutions on this way because you get into the problem of higher rank graphs as well, right? No, of course, like there are some new solutions, but here like we are totally safe that we get new solutions because they come from this kind of quaternionic algebras. But now, so like cube, right? So finally, at the last day of the conference, we get a cube. It's a geometric. Yeah.
You begin with the cube complex.
So from the cube, from the cube complex, I describe those complexes which we get, and we define the new. So we have a cube complex which we already got, and that's why like I showed that slide that we have to work hard to get this kind of interesting cube complexes, right? That all those A's and B's, they come from this kind of groups which I showed. Like in this example, you can do more, but at least in this example, and in particularly this cube is related to the example which I the first like easiest three-dimensional example. So actually it consists of 24 cubes because I showed the example like several slides ago. There were only squares, but actually the squares we put into cubes. So you see how we get this picture also illustrates my previous examples that how we get cube complexes, because in the group so far I showed that all the relations look like squares, right? But actually you put to get the cube complex, you put them on the sides of cube, right? So here like saying A, B, and C. So I had relations containing like A, B, B and C, C and A, and you put them on the sides of the cubes. And in the example before, like we have 24 cubes. I think it's something like 18 relations, but they can be arranged in the cubes. But of course, with the cubes, your life become more complicated when you glue the cube complexes, because what is also important that you have the faces. Yeah, you will have in those 24 cubes, you will have a lot of faces which match, and you have to glue the matching faces. And then like you have like higher dimension links and so on, like which are flag complexes and so on. But what is nice that in this series of arithmetic groups, which I described, you get this kind of all this compatibility on the level of cubes you get from the quaternion algebras. It's really kind of almost miracle that everything works. But how you define here the R matrix, you read it from the cubes saying, let's have, because also as we know from Fabien's talk, we have to find this bijection or like R matrix for the Young-Baxter equation. So we take a label of a square, but then we define it in this way that R of, I j xj equals to the the inverses. So in a way, to do this a matrix, it's almost like indeed construct a high rank graph that, for example, you say like a1 b1, and then you have b2 inverse a2, because you see the set x for the Yang-Baxter, it's the set of labels of the edges and the inverses, right, as a label. So I mean that we have a1 and a1 inverse as well. So actually twice more. So again, an exercise, we had like 9 different letters. We have like in the example I showed before, a1, a2, a3, b1, b2, b3, and c1, c2, c3. But then in the set X, we have 18 because there are inverses as well. So your matrix is going to be 324 by 324. And this is also what is new, that usually it's like the sets of solutions. The size of X is usually small, but here you get it like grows very fast. You get even like with the easiest example, you already get the R matrix, which is 324 and 324. Okay, are there any questions about this Yang-Baxter thing? And so this is not just a Yang-Baxter in a way, but this is illustration how this compatibility condition on the level of cubes work. That, like I think someone already mentioned that you look at the path going from one vertex of the cube to another, and then you apply all those operators and you apply the rule how we construct it. So like here we have like a 1b1c2. When we apply this operator on the left, we get c4 b2a1 inverse. But then if we apply this other operator again to a1 b1 c2, we get the same path as well. And again, the group G and can be regarded also as a new invariant, and saying from them those groups which we get from arithmetic, they are so-called like just infinite, and they have like nice invariants. They are, for example, they are different from the structure groups because they always have finite abelianization, and this is like one of the way to distinguish the equations.
How do you find gamma? The group gamma?
The gamma, but the gamma is the one with the fundamental group of the complex. Yeah, it's the fundamental group of the complex. More questions?
So
Okay, yeah.
So you say you can compute the abelianization.
Yeah. And no, not necessarily easy. Theoretically we know that since the groups are this kind of lattices in arithmetic sense, right? Then it's like the abelianizations are finite, and it's not an easy fact. It again goes back to Margulis, to a different set of work of him. Like it's one of the things which he got Fields Medal for. It's called like Margulis normal subgroup theorem, that those kind of nice arithmetic lattices, they don't have normal subgroups of infinite index. They have a normal subgroup, it's either the group itself or it has a finite index. So so the abelianization. So as I said, that there is a lot of structure which coming from arithmetic which you can use, including those spectral properties and so on. So actually to prove those kind of spectral bounds, you have also like Drinfeld hidden somewhere, like which is really like almost incomprehensible. It's another kind of Fields Medal thing, but okay, if it's correct, a lot of people use it, so we use it as well. But now let's finally come back to the higher rank graphs, and I'm very happy that I don't need to spend much time on this definition because it appeared already in so many talks that I think by now everybody knows it, and everybody knows that it's a bridge between like saying cube complexes and sister algebras. And so let me state at least one of the results for the specialist, because who knows, maybe I will not get through the next definition. So at least that we have some results about this is again for the experts. So what happens that there is a work of Nadia Aidan Laka, who's like, there are many, it's very collaborative community that you can so what they do, they use the spectra of hiring graphs to find like new examples of von Neumann algebras of K graphs. And what is of course fascinating in this paper of the authors I mentioned, that they have a construction of von Neumann algebras, and they have a criterion depending on the graph. How do you find the type, right? So for me, it's like almost a miracle. But then what was good that since we have this like nearly infinite, it's infinite supply of hiring graphs, just by tweaking the hiring graphs, we can have like a lot of examples of lambda, and I think one can do even more, but it's still quite a few of possibilities for this kind of three lambda factors. I know that in factor theory people like probably like 2 factors, but for me it was like still quite nice that you can vary this lambda in the three factors quite a lot. Okay, but the main thing which I would like to bring to this audience, it's alternative definition of a K graph which doesn't use category theory. Of course, in this community, everyone is happy with the categories, but I think that it's not everyone in the world, not every even a good mathematician in the world is familiar with the categories, because of course the definition of a K graph looks shorter than this one. But yesterday, for example, in a talk of David Patsk, he used several slides to get actually to start working with the K-rank graphs. But this kind of information here, okay, we stick for the finite case for the moment. Of course, it can be generalized, but let's stick to the finite data. Now, of course, the K-rank graph is not finite, but we capture this information, and then this is kind of equivalent to having a K graph. So what I mean, we have a directed graph with a finite set of vertices, finite set of edges, and then we have a disjoint union of the edges. And what also probably we should even modify, no, not even modify, but just to emphasize that you can think about each EI as an alphabet, and the edges of our graph are marked with letters, different letters of different alphabets, and in such a way that if we have 2 different edges, then they are marked by different letters of this alphabet. And then we look at the directed paths of length 2, and we look at such paths of length 2 which start and finish at the same point, and we require bijection somewhere like phi between those paths of directed paths of length 2. And then this is of course like prototype of the commuting squares, but just we have it in the finite setting, the phi of xy equals to y prime x prime for unique pair. So we have this change of the colors, which of course like by now everybody is familiar with. But then we have this second condition, which is like a cube condition, where if we draw, so the idea of this is kind of just formal like in many of Aidan's papers and of all collaborators on higher rank graphs, that what does it mean? That your commuting squares have to match on the sides of the cube. And you may say, why do you need some kind of alternative definition? But so you see what happens, that the K graphs, some kind of K graph like structures, appear in completely different fields of mathematics, and you can associate, because what is nice, if you find a structure of the K graph somewhere, then you can already define the sister algebra, because fortunate for us, there are so many nice papers. And like really very recently, I came up with some kind of dynamical system connection, and I, of course, like I even didn't plan from the very beginning to tell all those details about dynamics. But nevertheless, there is there is nothing which looks like higher rank graphs at all, but there is a certain structure when you say, okay, this looks like we can use this as a vertices in our construction with Nadia, and then there is some kind of incidence relation where we can theoretically think about it as edges, and then wow, you have a sister algebra. Because of course, like sometimes like to get to the categorical definition, it's very hard if you have like one complicated world and another complicated world, and you have to match them. So you want to have something like elementary in between, because like saying, for example, this definition is very easy even to check like by computer, right? You can just kind of write easy programs to get something of this kind, and then you have generators and relations of your sister algebra straight away for free. But I would like to finish with just it's Bondarenko, Grigorchuk, and myself. It's a work in progress. I hope to finish writing by the end of the summer, but there are more and more things which we add, because suddenly there is this new connection with dynamics which appeared like almost out of the blue, and then there was a place which I didn't know how to prove, because it's really hard, right? And even many of my new colleagues working in dynamical systems in New York, they don't believe that one can really get something n-dimensional with something which is called like mixing. But apparently how I can prove this mixing in n dimensions, that there is something which doesn't look like a higher rank graph at all, but then you kind of find that it's indeed a higher rank graph at all. And then there is a paper of Kumjan and Pask where they had a connection with dynamics, and they say if there is such and such a graph with such and such property, then you would get mixing. There were no such examples in the literature because they are really hard to get, but so it's like very, very good, one can use it. And this is like, okay, Alejandra is not here. It's like almost like answer to her question. She was asking like about bireversible automata. So actually, it's one of the definition of n-dimensional automata, which we can, of course, it can be more general, but this is something which works, and which again works using cube complexes. Then when we have this k-dimensional graph, which we defined with Nadia, but then if in addition, any two alphabets generate a bireversible automaton with an infinite group generated by this automaton, then we call this ND automaton. And what is, of course, it's like every K graph can be in some sense considered as n-dimensional automata. And there is even a paper of Ben Steinberg, Rue Excel, which they never published because they just say, okay, let's look at the chi-rank graph as automaton, but then you somehow start missing some of the dynamic properties. So you have to have a little bit more. So, but what are the good news here? Again, I don't say that it's all nice automata, it can be more. But saying if again, as this bioreversible automata, we take the automata which are which come from those cube complexes, then you get something nice. And again, what was here, like probably my last remark, that why it's not completely like easy to get whatever, right? That's saying to get the groups defined by automata, why it's not easy, because actually there is a result which tells you that, but by the way, the automata you get like similar, like in the talk of David Pask yesterday when he was talking about this kind of states and so on. So like, I don't have any time to remind it again, but there is this kind of relation with punctiles and automata. And what you, there is really quite remarkable property that if you have like your automata and you get the punctiles and you glue them, like I was showing before, like the letters with the same labels, respect and orientation, you get a square complex, which has a fundamental group as well. So in a way, you have two groups in the same time. You have this fundamental group, and you have the group defined by automata. And then this group defined by automata is infinite if and only if the fundamental group of the complex is so-called irreducible, which cannot be presented even virtually as a product. And there are only even two-dimensional, okay, there are only two of them. The example which I showed, and there is another one, which is due to Danny Weiss like many years ago. So it's in a way like yesterday, like David mentioned that there are, okay, so many of like hiring graphs at all, but what I would like, another notion which I want to show is like irreducibility. It's something which saying essentially k-dimensional, which cannot be presented as something like of smaller pieces, right? That not even the object itself, but even it's some kind of cover cannot be glued from smaller pieces. Okay, thank you very much for your attention.